It's my pleasure this morning to introduce our speaker, Professor Murat Arcak, who's a professor in EECS at UC Berkeley. His research focuses on dynamical systems theory and control with a wide range of applications, including everything from synthetic biology to multi-agent systems to transportation. Professor Arcak's work has been recognized by a number of awards, including the Ekman in 2006, the Control and Systems Theory Prize from SIAM in 2007, and the Antonio Roberti Young Researcher Prize from the IEEE Control Systems Society in 2014. And this morning, we'll get to hear a bit about Professor Arcak's work on control for cyber-physical systems. With that, I'll turn it over to you, Murat.
Thank you, Lillian. Thank you for introducing me. This will be a little interesting, but we'll see how it works. So I was actually thinking about my previous in-person visits to UW, and I was there spring 2009 to speak, and then spring 2015, and now it's spring 2021. So we have a perfect pattern here. So by that calculation, I guess next time will be 27 spring. So can we first make sure you see my screen? I mean, you probably see the.
Yeah, we see the presenter.
Okay, and maybe someone in the audience knows how to get out of this, but I personally don't. So I guess we'll go with this. Okay, we'll go with that. All right, so yeah, so I'll talk about hierarchical control for cyber-physical systems, and a running example of this will be traffic management. And for those of you who are curious about the next slide, I guess you're able to see it on the side. So the motivation is cyber-physical systems, and to me, a description of what cyber-physical system means is a large system that integrates many components, and therefore it is a large system. And in addition, a system that must satisfy complex requirements. So we have a large scale system and complex requirements, and the design and verification methods we have available in control theory do not really address those effectively. So that's the main motivation for this talk. How do we achieve scalability, and how do we address complex requirements? So we'll try and do this with hierarchical approaches in this talk. And as I said, the running example is network level control, road link level control, and vehicle level control, merging all these levels in traffic management. So the outline, first I'll talk about hierarchical control using abstractions. And there'll be some examples of this, including vehicle level control and reactive signaling at intersections. In the second part, since Lillian is there and she loves game theory, I thought it's obligatory to say something about game theory. So I'll talk a little about population games and how we ensure convergence to Nash equilibria when we have dynamical models, not just static models, in which the users, the agents, get to revise their strategies. So those are the two parts. First, I'll start with hierarchical control and the idea of abstractions, which is critical for that. So hierarchical architectures are very commonly used in controlling large systems. You can say it's ubiquitous whenever you have a complex system that you're dealing with, from the internet to anything you can imagine. So this block diagram here is more in the sense of perhaps autonomous driving or autonomy stacks. So we have definitely feedback control, but that's only one layer of the whole picture. Above that, we also have a planning guidance layer. This may also include supervisory control. And at the very high level, you may have a high level decision-making layer where you may be doing routing, or perhaps dealing with contingencies if you're dealing with autonomous driving. And of course, at the very bottom, you have a physical system that you have to interact with. So one of the critical questions is, how do we ensure that, how can we make formal guarantees about the whole stack? despite all the semantic gaps between all these layers. But this question was posed by my colleague Pravin Boraya in an early paper. How do you reason about the multi-world view of a system when you have multiple layers and each has its own semantics? So I compared this to this Norse mythology tree, Yggdrasil, which has many layers in it, different worlds. Midgard is where we live, and above us is Asgard, where gods live, things like that. And this tree combines them. So essentially, we want some kind of system theoretic notion of the Yggdrasil to be able to reason about different layers. And we will do this using abstractions in this talk. So first, I'll tell you a little about discrete abstractions. So the idea in discrete abstractions is to start with a continuous state model, like the ones we use in control theory very often based on first principles physics and so on, and try to represent it as a finite state model. The reason we want to do this is, as I alluded to before, we want to be able to deal with complex specifications, and the formal methods literature from software and hardware verification deals very effectively with these problems. Requirements expressed in temporal logic, for example, they can deal with those. The problem is, in that literature, you invariably have a finite state model. So how do we bridge the gap between these two approaches? That's where discrete abstraction comes into play. So we basically want to take our continuous state model and represent it as a finite state abstraction, design control actions for the finite state abstraction, and then refine them to the continuous state model. Okay, so the discrete states basically are partitions of the state space in the continuous model. Okay, so we partition them into cells, and each cell becomes a discrete state. To find the successors of a given discrete state, a cell, we do reachability analysis to see what other cells you can transition to under a given control. So that's one of the key ingredients of the abstraction, the reachability analysis. And then we get a finite model out of this, and that model will be amenable to formal methods from software verification or what have you. The formal guarantees we obtain for the finite abstraction carry over to the continuous state model under appropriate simulation relations between those two models. And there are very many variants of those. Perhaps the most current and most inclusive one is one by Günther Reisig that he published in 2017. So the main idea in discrete abstraction is, and the synthesis is illustrated at the top. So you have a continuous system color coded into 4 cells. Okay, so each of these cells will become a discrete state. So this is a stylistic description of what kind of trajectories you can have when you apply input U1 out of a quantized set of control inputs. And then the transitions that this triggers are to the yellow and purple cells, because the actual reachable set, which is in green, overlaps with those. And therefore, in our discrete abstraction, we direct transitions from the gray to yellow and purple. And let's say under a different control U2, you can transition to red and purple. So that's what the abstract model does. And the third image here on the very right is the synthesis step. It's extremely simplified, just for illustration. Let's say you want to avoid unsafe sets, and let's say the red region of the state space is unsafe. And clearly, input U2 can take you to that state. So you V dot U2. Okay. So of course, you can deal with far more complicated specifications than just safety with this approach. It's just that the synthesis becomes more complicated. So a little bit of history of this approach. In the 1990s, papers started appearing that partition the state space and use hierarchical control ideas. And in the past 2 decades, there have been a lot of advances. And here below is a partial list, by no means exhaustive. There are other authors, but those were the ones that came to my mind that fit into 2 lines. Basically, that was my criteria, nothing more complicated than that. So very interesting and appealing concepts emerged out of these studies, but still there are many computational bottlenecks in making this be applicable to even moderate sized problems. The problems start with reachability that I said you have to do many times to find the discrete abstraction. That already is not known to be a scalable thing. And even if you could do that, the more continuous state variables you have, you're going to be dealing with an exponential growth of discrete states. So how do you deal with those? How do you even store all the transitions? How do you compute them? So there's an explosion and there's the associated memory requirements. So to deal with that, we take advantage of system structure. So this is one of my favorite lines from The Simpsons. Um, so take advantage of a situation in some way. In this case, system structure allows us to do that. So probably the main bottleneck is still the reachability analysis. And to be able to deal with that, we have developed a number of fast reachable set computations. One of them is based on the idea of monotone systems. These are order preserving dynamical systems. And with Sam Coogan, who is very familiar to some of you in the audience, we worked on methods of using monotonicity as well as some variations, including what we called mixed monotone systems. So with this, we obtain interval outer approximations of reachable sets with very few computations. And under some conditions, these are also the tightest bounding boxes of the actual reachable set. The reason these intervals are suitable for abstractions is because the cells usually we take are themselves multidimensional intervals. So this gives us a very convenient computational structure with which we can find the successor states. In other work, we use the theory of contraction. This basically is a theory that looks at trajectories of differential equations and characterizes how far apart they can grow from each other. So with this, we developed a sampling-based strategy to compute reachable sets. We basically take samples, see where the trajectories land, and then we give guarantees of how the trajectories that we did not sample, how much can they grow apart from the ones we sampled, and that gives us a concrete outer approximation. And finally, we took recently the sampling ideas further and started using statistical ideas, including pack learning, probably approximately correct learning theory. So besides making reachability faster, we have to still deal with the explosion of the discrete states. So in this second bullet that I referred to, we deal with sparsity-aware abstractions. So yes, we can do reachability computations faster, but a more important question perhaps is how many times do you have to do it, right? In this work that I'm alluding to, we actually take advantage of the sparse structure of the system equations. And we see that we don't have to do as many reachability computations as we normally would if we did not have this sparse structure. So we took these monotone systems ideas much further. So when the requirements themselves have a directedness that's compatible with the order preserving nature of the system, we can actually make things much more faster and also more scalable by exploiting this monotonicity. For example, we introduce notions of sparse abstractions where we only keep track of the most extreme element that we can transition to, and we know that everything else will be will be lower than that with respect to a partial order, and that becomes critical in reducing the number of computations. We also developed lazy control synthesis algorithms, again for monotone systems. And these ideas actually come in very handy when dealing with autonomous driving scenarios, because a lot of times you have these monotonicity properties implicit in these scenarios. For example, if you have a vehicle following scenario, if you start out with a higher velocity and your goal is to avoid a collision with the vehicle ahead of you, if you know that you're keeping a long enough distance that works with a high velocity, with a lower velocity that will already work. Okay, so monotonicity is basically a generalization of this simple reasoning about. So that way, when you're doing your synthesis, you actually can simplify your task a lot. All right, so this was the vehicle level application. If we go one step above to link level, where we have to deal with signal controls and things of that sort, we again make use of these abstraction ideas, in this case, discrete abstractions. So a lot of the signal timing plans that are currently done in practice in transportation are based on steady state assumptions. Okay, so you assume the demand and the conditions are all in steady state, and you tune your signal scheme perhaps to time of day, but still assuming a steady state profile. The question is, what happens when there's a sudden change in demand, when there's a transient situation? So the tools that are available are not applicable in this case. So our idea in this work was to develop reactive signal control strategies that do not assume steady state. And what we do is we express the requirements in terms of finite horizon temporal logic. So requirements may be things like dissipating queues, avoiding saturation, or other things that you can think of. And then we pursue reactive synthesis using a finite abstraction of the flow dynamics. So the figure on the left illustrates this idea. So the arrows basically represent the flow of a nonlinear dynamical model of the traffic flow. And we represent this with a finite state abstraction. So the boxes that you see at the bottom, you can interpret this as, low occupancy in link 1 and low occupancy in link 2, if you were looking at this lower block. When I move my cursor, can you see anything? Or no?
Yeah, we can see it. Yeah.
Oh, okay. So this box will be low occupancy and so on and so forth. So we want to see the transitions until under given inputs. The inputs in this case are the states of the lights, green or red and so on. Okay. And this we use as a synthesis tool at the abstract level to guarantee the temporal logic specifications. So in this paper that you see on the right, we explain all these concepts. We also give in sidebars a review of the necessary formal methods background. And some of the ideas, such as using monotonicity or for abstractions as well as for reachability, they actually came from this application because these flow networks have certain monotonicity properties that come naturally with them. So another situation we look at is the case of continuous abstractions. So the motivation for that is, actually there are several motivations. So in this case, instead of representing a continuous state model with a discrete state one, we represent it with a smaller, simpler continuous state model, a low fidelity model. There are many uses of this. For example, it could be an intermediate step if you wanted to do finite abstractions. If the discrete abstraction method is not applicable to the large scale system you have, you may first want to consolidate it into a simpler model to which you can then do discrete. So it can be a connector that way. But this is of independent interest as well. For example, with this, we can do planners for autonomous driving. The low level model, the low fidelity model, can be used for, say, planning by MPC or other planning methods. And then it can be refined to the actual control. In this case, what refinement really means in this scenario is it's a tracking controller. So the low fidelity model, you design a planner based on that. And the refinement controller makes sure that the trajectories of the low fidelity and the high fidelity model remain close together. So it's a sort of a tracking idea. In other applications, which I'll talk about briefly, we also use this to aggregate large networks into smaller ones. So how do we make sure that the low and high fidelity models give us trajectories that remain close by? We use basically dissipativity properties. We use a function V that Girard and Papas in a 2009 paper called a simulation function. So it's like a Lyapunov-like function, I would say, that satisfies this inequality here. I will decipher this in a second. But first of all, what this function v accomplishes is it's basically serves as a metric of how far apart the outputs of the low fidelity and high fidelity model are. The second inequality here tells you that if v is small, essentially this difference between the two outputs is going to be small. Okay, so you can ignore the beta. These are nonlinear control theoretic jargon, but that's basically the essence of this idea. And the inequality at the top shows you that v would actually diminish along trajectories. One of our contributions here was to allow for a residual term here. So we don't necessarily need the function v to diminish to 0. We can actually allow for a little bit of leeway. And with that, instead of getting exact simulation relations, we get approximate simulation relations, and that's good enough for our purposes. Okay, so that small residual term actually does wonders when you're actually applying this to practical systems, because without it, to obtain these types of conditions without that residual term, you would need strong model matching conditions. And these are very strict geometric requirements on the model of the low fidelity and high fidelity. You basically want to assume that you can embed the dynamics of the low fidelity model into that of the high fidelity model. Okay, so what we are doing here with this residual term is we're relaxing that. We basically ask for closeness of the two behaviors. So one of the applications of this is to motion planning. So the abstraction is a simpler model, and we can use it, for example, with MPC for planning purposes. Now, the computationally heavy part of the work is in finding these simulation functions and extracting from the simulation function error bonds between the planning model and the actual tracking model. So that computation is done offline. So the real-time computations will be basically MPC, okay? And the planner, the MPC controller, would know about the error bonds, and it would accommodate those error bonds. For example, if you're looking at the scenario on the right here, where you're trying to reach the blue set while avoiding the gray boxes, then what you would do is you would shrink the target set by an amount of epsilon accounting for the tracking error, and you would bloat the obstacles, so you make sure you avoid them despite the error in the tracking. Okay, so this was presented at the IFAC World Congress last year. It was motivated by autonomous docking, which remains a difficult task, and a lot of people, captains, I've been told, do this manually to this day. So there's a picture of me on the left trying my hand, not on the real ship though. It was a simulator, very cool one, but they wouldn't let me mess with the real ones. So there's a lot of give and take in this procedure. So you don't want an overly restrictive planner, right? So you want to get small error bounds. So we developed some procedures in this paper presented at ACC last year to get tight bounds and to obtain maximally permissive planners that are not overburdened by these epsilons bloating and shrinking. So we want to minimize this epsilon, and we want to make sure that we can have as large a planning space as possible, so the planning task is more agile. And then the next application of this is to network aggregation. Same framework, again, continuous abstraction. This time, the concrete model is a large-scale network model with many agents in it and interactions. And the abstract model becomes an aggregate one where multiple nodes are consolidated into a super node, so to speak. There are precedents of this in power systems where people would take generators that swing together and merge them into a super generator, so to speak, for purposes of quick simulations, contingency planning, and so on. So we developed this approach of continuous abstractions, and we presented aggregation in this paper by Smith, Zamani, and myself as a special case of this, and we had some applications, including building temperature regulation. So instead of dealing with temperatures of individual rooms, you can represent whole wings of buildings with an aggregate temperature, and then design controllers for those aggregate models, and then refine them to the room level, and still maintain guarantee your requirements. And we had examples of signal temporal logic requirements for heat regulation and so on. I've been using similar ideas a lot in dealing with multicellular synthetic gene networks, especially in pattern formation. In this case, we lump certain cell types into supercells, again, for the purposes of simpler modeling. And we use aggregation concepts there as well. But I'm not going to go too much into that. All right, so before I start the second part, and I'm already, I guess, well, it's not too bad. It's been half an hour. So I have a little intermezzo here. So in the next part, we'll go into network level control. And if this will play, I want to show you a demonstration of platoons of vehicles that we did in Southern California more than a year ago. It was shortly before the COVID closures. I remember people were already talking about COVID at the time. So it was the videographer's idea that I come out behind the cars. It wasn't my idea. So what we did there is the following. So platoons of vehicles are vehicles that automate their, that maintain a constant headway as they move along. And you'll see this now in this video. So these three cars are the ones that we are in, but we are not really driving. We're only steering. The longitudinal control is done automatically. So these vehicles are talking to each other, and they maintain a 6 meter gap between them. That 6 meter gap is quite comfortable when you're stopped at a light and when you're accelerating. But when you reach the speed limit, which was I think 45 on this road, it gets pretty spooky. It's serious tailgating, and there's really not much room for error because you're very close to the vehicle in front of you. So why do we do this? Why do we want to keep 6 meters as we accelerate through an intersection? The purpose is to remove the so-called slinky effect, right? So you wait at a red, right? And then it turns green. The guy in front of you takes his time to slowly start moving, and now you take your time. So if you look at it from above, like from this quadrotor video, it looks almost like vehicles connected by strings, right? So it's stretch. And that's a huge loss of capacity at intersections. With simple calculations, you can show that you can double or triple intersection capacity, which is one of the biggest bottlenecks of the roads, if you can actually move them as like a train, as a rigid body, maintain a constant distance. That's basically what we are doing here. Platoons had been demonstrated earlier by my colleagues, but these were on freeways, and the technology at the time was very different. So in this case, we are basically using off-the-shelf tools, and then we are doing this in urban traffic, going through lights, and these vehicles are also connected to the traffic lights, and that's why we did this in that road in Southern California, because our collaborators had installed the necessary equipment on at the traffic lights. All right, so with that, I will stop talking about vehicle level or platoon level issues. I also briefly talked about road level issues, which include signal timing. So we'll move up to the network level, the routing level problems. And for that, we will get into game theory a little bit, but not the usual game theory with player one, player two. This is what we call population games. It is the continuum limit of very many players. Okay, the more players you have, of course, the strategy set and the possibilities will explode. And so the continuum limit, the population games, provides a convenient approach to large numbers of agents. So in this setting, agents are anonymous. You don't care who they are. They are basically a population, okay? And they have strategies. You don't keep track of agents one by one. Instead, you keep track of what fraction of agents is choosing which strategy, okay? And that way, basically, you use calculus, And you also use dynamical systems theory if you're allowing for strategy revisions by the players. There is a long history to that. It's very convoluted history too. It involves evolutionary biologists coming into the picture at some point, trying to make sense out of Nash equilibria and introducing population dynamics and so on. One of the biggest applications is to congestion and routing in traffic. And the mention of this goes back to a 1956 book on the economics of transportation by Beckman and his co-authors. So basically in congestion games, you have a certain demand for an origin-destination pair. In this case, the origin is this corner here, and the destination is here. You have 3 routes connecting them. So these routes are the 3 strategies you have at your disposal, right? So again, we don't count vehicles one by one. What we care about is what fraction of the demand, what fraction of the flow is taking route 1, what fraction is taking route 2, and so on. And x1, x2, and x3 represent these fractions. And naturally, because of the way we are defining these fractions, they have to add up to 1 or to the total demand, if you haven't normalized it. They have to live on a simplex. So that becomes sort of our state space, and we treat x1, x2, x3 as our state variables. So you can also have multiple populations. Multiple population in this routing scenario could mean different origin destination pairs, because then you have different routes, different strategies available to you. The basic assumption in defining a population is uniformity and anonymity within that population. If you have different choices or different behaviors, then you have to split the agents into different populations. So if you have multiple populations, then each of them will have a social state vector that will live in a simplex. So the overall state space will be the Cartesian product of the simplices for each population. And then you have a payoff. Payoff tells you what's the benefit of choosing one strategy, one route. And that's a function, of course, of the overall state. It depends on what others are doing. If nobody is using your route, chances are there is no congestion on it and you're better off, right? So that's why this function f, the map f, the payoff map, is a function of the social state. And it maps to Rn because it enumerates the payoff for each of the n strategies that are available. So going back to the routing example, x is a vector of the route flows, and R is a routing matrix that has an entry of 0 or 1 in each place, and it tells you which route is using which link. So when you multiply R and X, it basically gives you a vector of link flows. How much flow is there on one link? And then these go through these delay functions. There are many options for choosing these delay functions, but what is important for them is that these are increasing functions. So what that means is if there's more flow on a link, the time it takes to traverse that link is going to be higher naturally, right? So with that, here you generate a vector of the delays for each link. And by multiplying with the transpose of R, you actually generate a vector of the total travel time of each route. And the negation of that, since we are dealing with payoffs, which is supposedly a good thing, whereas delay is a bad thing, we negate the sign, and that gives us a vector of the payoff. So that's the structure of the payoff in congestion games. All right, a couple of very quick notions. If I give you a vector pi of payoffs, okay, so there's a notion of a best response to pi. So x in the state space, x bar rather, is a best response if it satisfies this inequality for an x. And naturally, it's not a very complex optimization problem. It's an obvious one. If pi has a single maximum entry in it, an entry which is bigger than all of the others, and obviously the solution in that case will be the corner of the simplex that coincides with that entry in pi that's the largest, right? That's how you maximize x transpose pi. If you have two entries that are the biggest but equal to each other, then x bar will be the whole edge connecting those two corners of the simplex and so on. So that's the notion of best response. It basically tells you what agents would naturally do. If pi is the given payoff, why would they choose an inferior payoff, right? They would all flock to the large payoffs. And that leads us to the definition of a Nash equilibrium in the context of population games. And these are also called user equilibrium or wardrobe equilibrium in transportation literature. So we basically say that X bar is a Nash equilibrium if it is a best response to the payoff at that state. Meaning that in the previous definition of best response, we took pi as a given payoff vector. Now we remember that pi itself is f of x, right? It's a function of the current state. So if you're at a state where the best response to it is staying where you are, that naturally is a Nash equilibrium, which means that given everybody else doing the same thing, as a single agent, you have no benefit changing your route or changing your strategy. You're going to be no better off as long as the others keep doing what they are doing. So the majority of the literature deals with equilibrium analysis of Nash equilibrium analysis of these games. Zillions of results on how efficient is the Nash equilibrium, how far away is it from the social optimum. People call it the price of anarchy. What is the ratio? Or how can you enforce, how can you make sure by mechanism design that the Nash equilibrium comes closer to the social equilibrium and so on. So a lot of these studies rely on equilibrium assumptions. They assume that you're under equilibrium conditions. Evolutionary dynamics model, on the other hand, accounts for the agents changing their minds and revising their strategies. Okay, and so a typical model you'll see is of the form that you see at the bottom, evolutionary dynamics model. So rho is basically the rate at which rho sub ij, the rate at which agents switch from strategy I to strategy J. Okay, so and x sub I denotes the fraction of agents in population R that are following strategy I. So then the first sum here that you see is the inflow to strategy I, how many new users are switching to strategy I. And the second term is the rate at which people leave strategy I to any others. Okay, so that's basically a mass balance type of equation, okay, which we represent. So we call this EDM, evolutionary dynamics model, and I put a superscript R when it refers to the Rth population. So an important problem in dealing with evolutionary dynamics models is to establish that you actually converge to a Nash equilibrium. So how would we establish that? First, we would have to plug in for pi, because pi is, after all, a function of x itself. It's given by the payoff map. So we have to interconnect those, right? Each of the p populations has its own evolutionary dynamics model, and they don't interact with each other directly except through this payoff feedback loop, right? So basically, we get a feedback diagram of the type that we're used to dealing with in control theory and dynamics. So the question is, do the associated dynamics take us to Nash equilibrium points? If the answer is yes, then it's a good thing, because first, a lot of the literature that assumes equilibrium conditions, they are justified. In fact, a lot of the criticism of equilibrium assumptions is also addressed, because in these evolutionary dynamics models, the agents are changing their strategies with myopic decisions. They don't have, perfect global information. They are just looking at, perhaps they are doing imitation. They are looking at their neighbor. Oh, that guy switched to this, he's better off. Why don't I do that? So there are simple myopic switching rules like that. And basically what this framework is allowing us to do is to establish that with such simple rules, you can actually converge to Nash equilibria. Okay, so that's why there's interest in the convergence to Nash equilibria problem. And it is not a given. There are many cases where, due to either the type of evolution dynamics or to the structure of the payoff map, you will not converge to Nash equilibria. So the beautiful book by Sandholm, late Sandholm, unfortunately, passed away last summer, on population games, has many examples of non-convergence. These can include neutrally stable cycles like the ones you see on the left, limit cycles like the one in the middle, even chaotic attractors are possible. So we can't assume that things will converge to the equilibrium. So then how do we accomplish, or how do we achieve convergence? How do we, under what conditions can we guarantee convergence? So this is a quick history of the types of results that are available. So one very interesting and influential paper by Hofbauer and Sandholm from more than 10 years ago shows that if the payoff map F has this monotonicity structure, it's not monotonicity in the strict sense, I guess there's a negative sign. So the negative of F is monotone in the sense of this inequality. Then they showed that a complementary property of the evolutionary dynamics model, which actually holds for various classes of revision protocols, guarantees convergence to Nash equilibria. So Jeff Shama and his student, presumably Fox, they looked at it, and they, being control systems theorists, they saw more system structure in there, and they identified the condition that Hofbauer and Sandholm had been using for the evolutionary dynamics model as a type of passivity property. Passivity is a control theoretic concept that actually came from passive circuits. I will not go into the details, but so they made this connection, and that connection gave us a very nice outlook on this theory and a new set of tools that we can deliver to strengthen the existing results. So with my collaborator, Nuna Martins, we actually made significant generalizations. So instead of passivity, we use what we call a delta dissipativity property. Dissipativity is a broader property that includes passivity as a special case. So we showed that we can, in fact, relax the monotonicity property as follows with this variational inequality at the bottom, where M is an arbitrary matrix. And of course, the evolutionary dynamics model has to satisfy a dissipativity property that's complementary to this property and has to have M in its definition, but I won't go into the details of that. But basically, monotonicity is simply a special case of this. If I take this matrix M to be 0, identity, identity, and 0, what that inequality here recovers is what we had at the top, okay? So this gives us a much broader swath of properties that we can deal with. So here's an illustration of why that's useful. So think about the congestion games again, but let's now assume that even though there is a single origin destination pair, and normally you would have selected one population, now we have autonomous vehicles and regular vehicles. Whichever type of vehicle you are, you're subject to the same delay. You're going through the same traffic. However, your contribution to the traffic is different. So the reason I played the video in the intermezzo was to show you that, with autonomous vehicles, you can actually maintain very short headways. So their contribution to the use of capacity is much less than the regular vehicles that take their time and exhibit this slinky effect. So there's an imbalance between what you're subject in terms of payoff and how you contribute to the resources, or how much you exhaust the resources. In this model of payoff that my colleagues Negar Meir and Roberto Horowitz published a year ago, they captured this imbalance by a factor mu. Okay, so mu is a number between 0 and 1. And it's a number that you can make smaller by keeping a shorter headway. Okay. And what this is showing you is that you have autonomous vehicles, the autonomous flows, and the regular ones in orange. Before we calculate the delays, we scale down the effect of the autonomous flow by a factor of mu, because they're, effectively, they are not going to contribute to the delay as much as regular vehicles. So we kind of discount them. So mu is basically a discount factor, okay? But at the end of the day, whether you're autonomous or regular, you're subject to the same delay. And if you look at the left side of this diagram, they both get multiplied by R transpose times the same delay, right? So This imbalance destroys the monotonicity property people had used earlier in congestion games. The payoff in a standard congestion game where mu is equal to 1 is monotone, and you can crank through the theory of passivity and so on. But with this factor, you lose that. But all is not lost is basically what we showed in this paper as an example. Despite the lack of monotonicity, we still have a incremental property of this form, where M is no longer zero identity zero, which was the special case of monotonicity, but now we have a weighting matrix W, which has that factor mu in it. And unless mu is exactly 1, which it boils down to the case of no autonomy, right? Then this is not a monotonicity property. It's a different property. Nevertheless, the evolutionary dynamics model has a dissipativity property that's compatible with this new type of incremental property defined by M. In fact, we don't even change the earlier assumptions people had made about the evolutionary dynamics model under the same conditions, which is a plain simple passivity property of the evolutionary dynamics models for each type of vehicle, for each type of user. We can weight things differently. So this is very much like, I don't know if Mehran or Behçet are in the audience, but this is very much like what people do when they study structured uncertainty in robust control, right? If you have structure in your uncertainty, then you can weight, you can multiply what's called a multiplier matrix and use that to obtain less restrictive robustness conditions. We do something very similar. Given that autonomous and regular vehicles are both have evolutionary dynamics models that are passive, and that comes for free with a lot of the revision protocol studies in the literature, then we can show that we can weight them differently and obtain a different dissipativity property for free. And we can do that to match it to the property that the payoff satisfies. And so at the end of the day, without adding any new conditions or adding any further restrictions, we guarantee converge to Nash equilibria in these mixed autonomy congestion games as an illustration. So what are some of the remaining problems and what are we currently looking at? So in what I presented above, the payoff was a map. It was static, okay? So our goal right now is to go from static maps to dynamical models of payoff, because it's not exactly reasonable to assume that the payoff is a static mechanism. It evolves itself over time. And if you specialize to traffic networks, there are many things that affect the payoff. For example, the queuing dynamics are an important contributor to how much delay you actually experience. It's not just the one function of the flow, right? So that needs to be taken into account. Once you start taking into account queuing, then you actually start realizing that this whole diagram has some control knobs in it that you can tune. For example, if you're dealing with queuing, you can also use signal control in a way that you shape the payoff. You shape the payoff dynamics to your taste to perhaps assign a desired property to the interconnection of the payoff with the evolutionary dynamics model. There are, of course, other control knobs, such as tolling, as well as information dissemination. How much of the information do you give away? Or naturally, how much delay there is in the information by the time Google Maps tells me how much, what's the delay on a given route. So dissipativity theory, which we used in the aforementioned result, naturally extends to these types of dynamics. So that's why we like it, and that's why we are continuing to work on it. And also it guides the design of some of the blocks that can actually be designed, as I mentioned. Going back to the earlier parts of the talk, hierarchical architectures are critical for cyber physical systems, and we've been using traffic networks as a case study throughout the talk. And there are a lot of research opportunities here for two things. First, how do you reason across different layers, across different worlds? Second, from a design perspective, how do you connect these different worlds, and how do you take advantage of information from one layer to another in designing for example, when you're doing routing, how can you take information from the signals and so on? And that's basically what I was showing you here with this block diagram, is a step in that direction, trying to connect the network level control to the layer below that. So that's the overall perspective. I hope, despite technical difficulties and you having to look at my notes, I don't know if I had any, and the next and previous slides, I hope you were able to follow some of this. And thank you again, Lillian, for introducing me. I'm happy to take any questions if you have time.
Yeah, thanks for a great talk. I'll open it up. I think we have a few minutes if people want to ask any questions. Go ahead and unmute yourself. There's no questions. I'll ask one. I'm glad you mentioned this dynamics thing at the end. So first of all, this is really cool with the this dissipativity stuff. I hadn't thought about that, but that's a nice connection to make. So one of the things we've been working on is actually situations where you're learning and using evolutionary dynamics for matrix games, basically. And we've been looking at the case where the matrix itself evolves over time periodically. And what we've been able to show is actually some negative results, that some of the regularities that you would get, things like time average convergence, recurrence, things like that, sort of fall apart. Even when you have like a periodic, you would expect those things to sort of persist when you have sort of a periodic variation in your dynamics. And I would imagine that in traffic, you kind of have these periodicities as well. And so I'm wondering, and so the types of games we've been looking at are mostly zero sum. So they're sort of the opposite of these potential or population games. So I'm wondering if you think that some of the nice results that you can get in the static case will persist in the dynamic case, or sort of what do you see as some of the technical hurdles?
Okay, good question. So I guess you're thinking about fluctuations in demand over the day.
Yeah, for example.
Yeah, that's a great question. So it really depends on what part of day you're dealing with. So if you're thinking about, or when the users get to revise their strategy, there are a lot of hidden assumptions in these evolutionary dynamics models that aren't necessarily paid attention to. So, usually it's a Poisson process with which, you have a chance to revise, right? But is that really reasonable? So that's the first thing that needs to be questioned, I think, when starting to answer your question. So, for some types of vehicles, you actually, if you're an Uber driver, right? So you have to actually first finish one trip before you embark on another. So that's not really a Poisson distribution. In some other literature, people simplify saying, okay, every morning is a new day. I have a new choice to go to work. I can take a different route. So if that's the case, then, you're looking at a different, so you're not looking at evolution over a day, but you're looking at evolution over days and days for that period of time, right? So it's a matter of how you interpret what the dynamics are. Are the dynamics evolving over the day, or am I splicing a certain hour of traffic day after day after day? So I think that's probably one way to look at it. But I think, one takeaway from your question is it is extremely important to understand the underlying assumptions that lead to these models. And without them, they are not particularly meaningful. Yeah. And that's a very good point.
Yeah, that makes a lot of sense. Any other questions from folks? If not, we'll wrap up since we're sort of eating into the next meeting. So thanks again for the great talk.